Hi, everyone. Thank you all for being here today. Welcome to the 2022 National Solar Radiation Database webinar hosted by the National Renewable Energy Lab. I'm Jess Townsend with the NREL Communications Department. I'm going to get us started with a few welcome and housekeeping items before turning the event over to our panelists today. Next slide, please. All right. First, this meeting is being recorded, and the webinar recording and this presentation deck will both be distributed via email after the webinar today and posted to the NSRDB website. Otherwise, this is a webinar format, so be aware that your microphone and camera are disabled. So no need to worry if you've accidentally unmuted yourself. We've already got you set. If you have a question, please submit it via the Q&A panel you can access at the bottom of your screen. If that box isn't appearing for you, simply move your cursor to the bottom of your screen and it'll show up. We have quite a big crowd here today, so we do have some people viewing via a YouTube live stream. For anyone viewing on YouTube, you won't be able to use the Q&A box because you're not in the Zoom with us, but we have added a questionnaire form to the event description box in YouTube, and it's also listed for you here on the slide. So it's the bit.ly/NSRDB. You are welcome to submit your questions there. And of course, anyone in the Zoom is also welcome to submit their questions there, and you'll receive a response from the NSRDB team. All right, again, we're going to save all of the questions until the end of today's event. We should have about 30 minutes left over at the end to take as many questions as possible. But welcome again, and I will pass the mic over to Dr. Manojit Sengupta. Dr. Sengupta, take it away. And next slide, please.
Thanks, Jess. And I'll quickly introduce our panelists today, and we'll get going. We have Dr. Tassos Golnas, who is a technology manager at CETO, and he is essentially the project manager for our NSRDB project. I am Manojit Sengupta. I am atmospheric scientist who leads this project, the NSRDB project. And of course, the NSRDB project is a pretty significant large project, needs expertise on various aspects of the science and engineering. So we have Dr. Yuji, Aaron Hapte, Grant Buster, Paul Edwards, Haiku Sky, and Nick Gilroy, who are part of the NSRDB team. Without their help, we wouldn't have had the success we have. But I'll now hand it over to Dr. Tassos Golnas to give us a quick introduction before we dive into the details of the NSRDB. Tassos.
Thank you, Manojit. We can go with the next slide. Great. So, you know my name. I'm Tassos Golnas. I'm a technology manager and currently acting program manager of the PV team at CETO, which is the Solar Energy Technologies Office at the DOE. It's my pleasure to give a brief introduction to the office and say a few words about National Solar Radiation Database, a project and a product that CETO has funded and supported for the past 7 or 8 years. Next slide. So what's the mission of our office? At CETO, we accelerate the advancement and the deployment of solar technology towards an equitable transition to a decarbonized economy by 2050. We do this in 3 ways, and we'll need to click 3 times to show these ways. Next slide, please. Okay, I missed something in the presentation, but don't worry about it. So we do this 3 ways, as I mentioned. We drive the technical innovation and the soft cost reduction that's necessary to make solar affordable and broadly accessible. We enable solar to support a reliable, resilient, and secure power grid. And we also support job growth, manufacturing, and the circular economy. We execute this mission by funding more than 400 projects around the country, which are led in roughly equal measure by the national labs, universities, and businesses, nonprofits, and state and local governments. Next slide, please. The office comprises 6 teams. 3 of them, you see them on the screen right now, are focusing on specific technical innovation, while the rest support manufacturing, soft cost reduction, and workforce development. Please click. You can see the other 3 teams in CETO. Next slide. So I know this roadmap slide is an eye chart, but I'd like to bring your attention to the top right. This portion underlines one of the key goals of the department for 2030. And namely, this is the acceleration of deployment of solar to levels that are 5 times faster than today. Next slide, please. Meanwhile, you can read about a comprehensive view of the role of solar in decarbonizing the power sector in the whole energy system by accessing the Solar Future Study. You can just enter the words Solar Future Study in your favorite search engine, and you will have access to the study itself, as well as other materials that are easier to consume. Next slide, please. If you want to learn about upcoming funding opportunities and other key activities from CETO, like active RFIs, we have an active one for PV system performance data that you can click on the link and have access to. Please, to do all that, sign up to our newsletter so you don't miss any news that come from the office. Next slide, please. And now for our feature presentation. For CETO, the NSRDB is a foundational program, a core project whose output supports strategic and tactical goals for the Department of Energy and the Solar Office. For starters, it supports numerous studies in the research community which rely on NSRDB for environmental input data that are relevant to solar energy generation. For example, any planning studies or deployment scenarios that come out of the labs and which involve solar generation, they use NSRDB for their input. Manager will provide more details for that during his presentation. In addition, the existence of this freely available dataset allows for the efficient creation of feasibility studies, which is something that's a key activity for the project developer community. And while the dataset cannot be used to generate bankable estimates of performance, it supports this, a scale that is necessary for the cost-effective growth of the industry. At the same time, tools like SAM, the System Advisor Model, and PV1s, both provided by NREL, have been equipped with the capability to leverage the NSRDB dataset, and they further lower the cost of early project development. Finally, the physical basis of the dataset provides transparency to the output and the product, and more importantly, allows the interoperability with other physics-based models for the atmosphere and the climate. This interoperability is more than skin deep, as it also has an explanatory power, often absent from empirical or statistical and data-driven products. Without further ado, welcome to the webinar for the National Solar Radiation Database. Manager.
Thanks, Tassos, for the introduction. Now we'll get into the core part of our presentation. So this is our webinar for the NSRDB, and let's get started. So next slide, please. So what we're going to go through today are the following 8 topics. Basically, the evolution of the NSRDB. We're going to talk about the model behind the NSRDB. Next is what's new over the last couple of years since we had our last webinar. So we're going to talk about our data quality and validation and how you can access the data through various portals. Finally, we'll conclude with what are you planning to do in the near future, and also some publications if you want to refer to the NSRDB. Next slide, please. So let's get started with the evolution of the NSRDB. Next slide. So the NSRDB was originally started in around 1994. At that point, there was no satellite data, and we used various ground stations. We did not have solar radiation though. It was other atmospheric data, and it was maximum most of the data at those 239 stations were modeled. Then, as our goal is to provide state-of-the-art data sets for research, we moved over to the satellite era, and we currently, what we have is a data set which goes from 1998 to 2021. Our satellite was originally 4 kilometer by 4 kilometer, half hourly. And currently our next generation or newest generation satellite is now 2 kilometer by 2 kilometer, 5 minute. And the data sets we make available from the NSRDB are at the satellite resolution. Additionally, I'd like to mention that this year we put in a significant effort to update all the data from 98 using the latest version of the model, the physical solar model, so that all the data produced has the latest physics in it. While 2021 has been released, we are currently uploading 1998 to 2020 with the latest data. It'll be soon be available, probably within a week. It's just a little slow process because it's a huge volume of data, but it'll be available probably within next week. Next slide, please. So now I'm going to quickly talk about what's behind the current NSRDB. It's the physical solar model, and as the name implies, it's primarily a physics-based model. As you can see, there are different layers in the diagram. The topmost layer is the source of data. The GOES is the satellite data. Then there's MERA2, which is a data set, which is a model data set available from NASA. MODIS is another satellite, which is a polar orbiting satellite. And then we have the ice and interactive snow and ice mapping for primarily to get our albedo. So, and the second layer is other products we derive from these different raw data sources. So for solar radiation, we do need the cloud properties. We need to identify whether it's clear or cloudy. We need the cloud properties. We need an atmospheric profile. We need the aerosols, the surface albedo, and of course, when there's snow, we need the snow albedo. So as you can see, all of this data is obtained and then fed into a radiative transfer model, which is an NREL developed, the FARMS model is an NREL developed model, which produces the global horizontal irradiance, the direct and the diffuse very quickly. So it's a fast model specifically geared for satellite applications. So next slide, please. Just a quick summary of what the FARMS model really is and what we've leveraged. Essentially, if you look in physics, we found that cloud transmittances can be parameterized as exponential functions of the cloud optical thickness and solar zenith angles. So that's what has worked in our favor. So from the atmospheric models, which are much slower, as we've developed this parameterized model, FARMS, so that we can basically process millions of pixels in a very short period of time. And that's what makes the current NSRDB product feasible. So next slide, please. So now let's jumping on to what's new since we had our last webinar. So what's new in the NSRDB? So I will go ahead and present some of it, and then Grant will take over from me. But please, next slide. As you can see, we originally had NSRDB coverage, which covered the Americas with the GOES satellite. In the last few years, we have and we're thankful to CETO for funding us to develop the fundamental research. So DOE International and USAID has recognized our capabilities and asked us to provide global data for areas of interest to them, and they have funded the development of data, the coverage in the green bar. box. The main thing is that the physical solar model is a universal model, so it can assimilate any geostationary satellite-based cloud properties. The only difference between different satellites is the temporal and spatial resolution, which influences the resolution of the final product. Next slide, please. So just a quick word about the Meteosat data covering the Indian Ocean. Right now, the time period is, we have 3 years of data, 2017 to 2019 at a 4-kilometer resolution and 4-kilometer and 15-minute temporal resolution. And there's a publication behind it. If you want to read more about it, it's there, freely available from the NREL publication website. Next slide. Then we have the Himawari, which covers China, Australia, Japan. There, as you can see, the Himawari covers the period from 2011 to 2020, and there are 3 satellites involved: the Himawari 8 with a 2-kilometer by 2-kilometer spatial and 10-minute temporal resolution. Then the previous satellites have a slightly lower resolution, both spatially and temporally. So it's 4-kilometer by 4-kilometer in 30 minutes. And then, of course, because we have 10 years of data here, we have also produced a TMY, which is available for our users. Again, there's a publication which you can freely access from the NSRDB publications website. Next slide, please. We also, for a project from DOE, there was a requirement that we be able to produce a long-term high-resolution data set for Puerto Rico. Essentially, what we did was we built a simple downscaling model which spatially and temporally downscales the data from 4-kilometer 30 minutes to 2-kilometer 5 minutes. This data is also available from the NSRDB database for anybody who's interested in the Puerto Rico region. Next slide. Then coming to the core part of the NSRDB, which is our GOES satellite. What we have since 2018 is 5 minutes. So there's 2 satellites, goes east and west. So the east satellite came on board in 2018. So we have 5-minute data from 2018 for the GOES east, and then GOES west came online in 2019. And so we have 5 minutes data. Of course, to maintain continuity, we produced a 4-kilometer 30-minute data so that we have continuity in our data products, but we also make available the 5-minute data at 2-kilometer resolution to all our users. We also produce a TMY every year. As we add a year of data, we produce a new TMY, which is made available to our users. Next slide, please. So this is just a quick, what do we get out of 5-minute data versus the original 30-minute or hourly data? As you can see in this slide, the observations, ground observations are in blue. Of course, there's variability. It's a point observation. If we are doing 30 minutes or hourly, which is the red or the yellow lines, as you can see, we missed a lot of that variability, essentially because of the low temporal resolution. With the new satellite at 5 minutes, as you can see in the green line, we are able to capture a significant amount of the variability we observe at the ground. So this is definitely a game changer for those who are looking at variations in solar radiation over the period of a day. So next slide, please. And finally, we also have made available UV from the NSRDB. So essentially everybody who needs to do any studies which require UV data can get this data directly from the NSRDB. It's a model we developed using smarts And then essentially what we found is that UV is reasonably directly related to the GHI, and the model is just based on that concept. We validated that model using actual ground data for a significant number of stations, and we found that the model is extremely robust. So especially if anybody is looking for UV dosage throughout the year, this is a very good data set to use for that purpose. Next slide, please. And then we have, as you said, what's new. So we originally had snow albedo, which is fixed at 0.86, which is pristine snow, with bifacial PV being of so much interest to our users, and all our users are using our albedo data set. We decided that we needed to have variability in the snow, and we implemented a new model, which is available through the newest version of PSM, and all of the data will be online soon. This model does is essentially varies the albedo based on ground temperature. The concept is that as snow melts into water, the reflectivity of the albedo goes lower. So this model essentially depends on the temperature, air temperature close to the surface. And it's a model which is used by a lot of people who in atmospheric science. So next slide, please. And now I'll hand it over to Grant Bester, who has done a lot of work in shaping the current version of the NSRDB. So Grant, take it away.
Thanks, Manjeet. So my name is Grant. I'm going to be talking about some of the work we've been doing on the cloud properties in the NSRDB, and then also some of the data quality and QA stuff. So the NSRDB is a satellite-derived data set. So we use cloud properties to do the rate of transfer. We see these clouds from space, from our satellites, and where we actually see these clouds is highly dependent on the curvature of the Earth, the viewing angle from the satellite, the geometry of the cloud, and then where the cloud is actually casting its shadow and it's affecting solar radiance is highly dependent on the height of the cloud and the position of the sun. So what we've done in the recent versions of NSRDB, which is reflected in the most recent data release, is implemented methods to not only parallax correct the cloud over the pixel that it's literally physically over, but then also apply the cloud properties to the pixel in NSRDB that it's actively shading based on the sun's position. So this gives us a much more accurate representation of the irradiance that's actually being observed at the surface. It really improves a lot of things like timing. So you get really accurate timing of clouds as they pass over and shade different pixels. Pretty cool model. Next slide. We've also implemented a machine learning method to predict cloud properties. So this is shortened to just the ML clouds model. There's a publication that goes into all the details of the model. We use a physics-guided machine learning approach, and we have a lot of rigorous validation in the paper itself. What I want to show here is that the two top images, DNI on the left and GHI on the right, you can see the old version, V312, where we had what are basically missing cloud properties. So our traditional algorithms were not able to determine the cloud properties based on the satellite images. And so that results in this really crazy oscillations that you can see in orange. And then using the ML clouds model as a gap fill methodology to fix those cloud properties, you can see it snap back up to that the green and the red data traces, which matches the ground measurements quite well. So that's pretty exciting. That helps our data quality when we're missing cloud properties, helps the data quality quite a bit. And then on the lower row, you can actually see that we've done some exploration of how this model does during all time steps, not just as a gap fill methodology, but how this model performs during all times. And actually, for the majority of times that we've examined, it performs quite well. You can see that the traditional methods were greatly underestimating the thickness of the clouds, whereas the ML clouds model is getting it pretty right on. We're still kind of evaluating this. So, in the paper and in these slides, we kind of call it V3 plus, as in like, we might release this as we might release ML Clouds as like the full cloud property model sometime in the future, but not now. Next slide. As part of this paper, we did a pretty comprehensive validation. There's 20 ground measurements, I think 20 ground measurement sites throughout the US. Right here, all you're seeing is the mean absolute error for DNI and GHI for time steps that are cloudy. So basically what you're seeing is the improvement over these versions, specifically for these time steps that are cloudy, improvements in the cloud properties, et cetera. And these versions, the subsequent versions are the shading model in v3.12, the ML Clouds as a gap fill methodology in 3.20, and the full ML Clouds in this future possible version of v3+. So you can see we've been making improvements to how we're interpreting these cloud properties and how we're applying them in our models. Next slide. So as part of all this work, we've been trying to get much more transparent and explicit about the data versioning and the software versioning. We understand that it's confusing how many improvements we're making and when we're applying them. So we've been working on this version log that is on the website, on the nsrdb.nrel.gov website. It's also part of the software now, and it's also part of all the data that we produce. So when you go download like a CSV of data, or if you go inspect the raw H5 files, it should have a version that corresponds to something on this version history, this version log. Most recent version is 3.22. This includes all the improvements that we were just talking about, and we're as Manjeet mentioned, we're releasing this this version for all data years. We're re-releasing 1998 through 2021. All updated with the latest and greatest, and hopefully it should it should improve the data quite a bit. Next slide. So I'm going to quickly talk about some of the data quality and validation that we've been doing to improve the quality of our data. Next slide. So we're releasing, I think the full NSRDB is around 200 terabytes of data or something crazy like that now. It's really hard to QA all 200 terabytes of data. You can't QA every datum literally, but we've been trying to improve on our quality metrics, and so this is kind of the current practice that we go through. The first is establishing physical limits before we actually run the physical solar models. This ensures that our inputs are sound. We run all of our models with processing quality flags. So if anything goes wrong in the processing, it's flagged in the output data, and I'll show you what that looks like. We then do some qualitative review, looking at just maps of the data through the year to look for kind of gross errors or weird patterns that come through. And then we do a ground truth validation that compares against ground measurement. And this is kind of the gold standard of, how well does the ratings data we're producing actually match a ground truth measurement. Next slide. So as mentioned, we get all of our data sets from a variety of different sources, MERA, satellites, et cetera, et cetera. These models and data sets in and of themselves are not perfect. So we make sure that we're making sure that we have appropriate physical values for all these data sets before they get passed into the physical solar model, so that we don't get any weird things with like negative aerosol optical depth or anything crazy like that. So that's been really good to improve the quality of the data. Next slide. Then this processing quality flags. So things go wrong like all the time. In the satellites, for example, I mentioned this gap fill thing where we're missing cloud properties. There will be random times where the satellite just doesn't return valid data. If there's extreme viewing angles or extreme solar zenith angles, the satellite can't return proper data, or our models can't predict valid cloud properties. So we have these processing quality flags that you see on the left. They're attributes of the data sets in the actual NSRDB files, and you can query them as you query data through the API. So it's worth looking at, especially if things like look kind of weird. If you were to look at Hawaii in 2018 for this 5-minute data set, we only had the GOES East satellite, so the Hawaii data is going to be nonsense, for example, and you'll see that in the data. But then you can also go look at the quality flags, and it'll tell you exactly why you're not seeing valid data. So 99.9% of the time, the data is of very high quality and it's totally fine. But for these weird examples, like when you're using the GOES satellite and looking at Hawaii, it's just, we won't have valid data there. Next slide. Okay, so validation, these are the 20 ground measurement sites that we're using. We've kind of expanded our ground measurement suite of sites outside of just the SURFRAD sites. We're now including a bunch of University of Oregon sites for the Western satellite and also sites in the SOLARAD network. Okay, so I guess it's just 18, my apologies. Next slide. We do a variety of validation metrics. On the left, you can see the mean bias error, mean absolute error, and root mean squared error, both for GHI and DNI. You'll notice that, right off the top of the bat, the DNI tends to be have higher error, which is, not terribly surprising given that as soon as a cloud passes over, the DNI basically drops to 0, so the relative error is going to be quite high. However, the bias errors are quite low. We try and keep them within 5% for GHI and 10% for DNI. The bias is looking very, very much lower for data from the newer satellites with the higher temporal and spatial resolution. So we're, the most recent data is kind of the state of the art, and we're expecting it to be much better and hopefully improve even more as time goes on. Next slide. Finally, just a look at the comparison between the old PSM v311, which was the previous data set that we had been releasing prior to this year, comparing to the latest and greatest PSM 322, which we are releasing now. This is just for 2019, so this is a 2 kilometer 5-minute data set, and you can see some pretty good improvements in the validation error, especially for these most recent satellites that have higher resolution. So yeah, we're really excited about the current state of the NSRDB, the level of quality we've gotten to, and we hope you appreciate it. Thanks. Next slide. I'm going to hand it over to Nick Gilroy for some data dissemination.
Thank you, Grant. Let's go to the next slide. So I will be covering data dissemination of the NSRDB data catalog. For context, the data can be accessed in 4 ways. First, directly through the website, nsrdb.nrel.gov, via the viewer. The second way to access the data is through our API. Next, through the Open Energy Data Initiative, or OEDI, which has the entire catalog of data hosted on Amazon Web Services, or AWS. Finally, the data is available via NREL's System Advisor model. So earlier this week, my team released a major update to the viewer. And as a result, I'll be spending the bulk of my time discussing those updates and highlighting key workflows. As part of the revision to the viewer, we also provided functionality to assist in generating queries for the API. And finally, I will briefly mention OEDI and when a use case would warrant that data access approach. So let's jump into the updates. So as part of the process to update the viewer, we gathered feedback from users and stakeholders alike. We also went back to the basics. What is the viewer? What problem does the viewer solve? And how do we know if we've solved the problem? So what is it? The NSRDB viewer is a freely accessible web platform that hosts the entire data catalog. What problem does the viewer solve? The primary purpose is to enable access to the data and empower people to answer questions they may have, such as, what data is available at my location? Or, how can I tell the extent of the PSM data? And how, finally, do we know if we've solved this problem? First, we wanted to do some revisions to reduce the number of clicks and needed inputs to identify a location of interest, a pin on a map, an address, coordinates, etc. Second, we know we solved this by the reduction of multiple entry points. So we've removed the data library section, the dedicated query tools, and the section dedicated to data download. We've now refined the viewer to be a single entry point and with the sole purpose of downloading data. So let me provide a brief orientation. We've simplified the view to show a single layer of data. And to provide additional context, we've added the extents of the models from which the data is derived. Hovering over an extent will provide the data characteristics, including the model's name, and temporal range of data available. To get started, I can type an address or a name of a location. In this case, I've started to type NREL, and I could use the type ahead to refine my selection to the NREL Visitor Center if I desired. Or I could simply click a location on the map and immediately pull up all available data sets at that location. To change the type of query from an address or point, you can click the drop down in the left of the search box. And once the drop down appears, additional ways to set an area of interest can be selected. So for an example, here I've selected point, which does allow for manual entry of coordinates in the search bar if a predetermined location has been identified outside of the viewer. And again, you're also able to click a location on the map that would drop a pin for that location. So once a location's been identified, the drawer on the left automatically opens. In this example, I identified a location that has 3 data sets available. If I had selected a location where only 1 data set was available, the model would have been automatically selected and I could skip this step of deciding which one to download. So let's walk through the rest of the form. Again, I need to select which data set I'm interested in downloading. In this case, I chose the recently released Himawari dataset. Next, I select which attributes I would like to be included in the download file. In many cases, the minimum required attributes to use the SAM model have already been selected for you, but additional attributes can be included. Then I'll select which year or years to include, then the interval of the data. In this example, I've selected 10 minutes. Second to last, I enter my email where I would like to have a link to access the data sent. And finally, once all required fields have been filled, the download button activates and I can request this data. So let's see this process in action. Here, we're downloading the new 2021 PSM data. I've identified a location in Brazil, and I choose the newly released PSM model, and I select all available attributes to download. I set 2021 for the year, and the interval is set to 30 minutes. I've input my email and click download. A confirmation notification at the top of the viewer is shared, and shortly thereafter, I receive the data as a link in my email inbox to download a zip file. The email will originate from a no reply at nrel.gov, and clicking the link will initiate the data download. I want to note, NREL does not share its email list with other organizations or companies, and your information is only used to provide download access to the requested data and to provide infrequent notifications when data sets are updated. If you want additional information, please see NREL security and privacy notices, and the link is provided at the bottom of the slide. Okay, let's see another scenario in action. This time a region query. So here I draw an area of interest on the map and select the data set I would like to download. This time, as I'm working through the left drawer, I'm notified that the area I'm interested in downloading exceeds the download limit. So we have download limits because the data downloads are a shared service. Currently, our storage archive contains hundreds of terabytes of data and is constantly growing. So to reliably serve dynamic segments of a data set of this size to a growing community of users, we've calculated the maximum capacity our server hardware can sustain. So let's walk through some alternatives on how to access this data. We can start by looking at the view code option. This new feature is designed to help bridge the gap between the viewer and the API by creating the query relevant to the location already selected in the map. The viewer then formats the request that our API is expecting. If you've not used the API, here is the link to sign up for an API key on developer.nrel.gov. Once you have an API key, you could enter it here or simply type in a placeholder. Next are 2 buttons, one to download the Python script and the other to copy the script to your clipboard. From here, you would have to run the script yourself, but we're hoping that we remove some of the burden on accessing our API by sharing the relevant formatting needed to make a request. So here's the resulting script copied into a code editor. Note, if you provided the API key, it was already placed on line 6, and if you also entered your email in the left-hand drawer, it was placed on line 7. If you did not, you'll want to update these in your script prior to making a request. Now you should be ready to make your first request and download data. I would also like to share the link for additional documentation around the API, as well as highlight that we've restricted the API in several ways, including the number of simultaneous requests a single user can make, the number of requests a single user can make in a 24-hour period, as well as the maximum size of a single request. So those rate limits are set at 1,000 requests per day, 1 request every 2 seconds, and 20 requests in process at once. For any questions about the API, please contact us at nsrdb@nrel.gov, and we'd be happy to help you and continue to refine the experience around the viewer and API. So, for users interested in accessing bulk data and have a use case where the API rate limits are too restrictive, the full data sets are available through the Open Energy Data Initiative. OEDI is a CETO-funded project that has been partnering with AWS to obtain free cloud storage to highlight DOE's high-value public data sets, NSRDB included. Accessing data via OEDI leverages the HDF Group's highly scalable digital service, or HSDS, and HSDS allows for optimized cloud access to the source HDF5 files stored on AWS. HSDS is essential for allowing access to the NSRDB, as it negates the need to download the entire more than 1 terabyte source file and simply access chunks or slices of the data that is of interest. So in conclusion, we've covered 3 of the 4 access methods for downloading data from the NSRDB data catalog, but we would like to hear from you and what else would be impactful in the viewer or API, and what would make a difference in your work. So again, please reach out to the team. The best way to contact us is via our email, nsrdb@nrel.gov. And so now, next slide, yep. Now let's transition from data dissemination and highlight some broader updates to the NSRDB website. The website is accessible at nsrdb.nrel.gov, and it's been updated to include a revised navigation bar along the top. Currently, we're on the home page. In the navigation, you can note the About page. Nested in that dropdown is a new page dedicated to sharing announcements from the NSRDB team. This page has all relevant updates, and the latest post discusses the newly updated PSM dataset in more detail. I would also like to note under the Datasets tab, everything I've presented is summarized in a page called How to Access the Data. Finally, to access the viewer, there's a call to action below the Welcome banner on the home page, as well as a dedicated tab in the navigation bar. I would also like to draw your attention to the banner itself. Now it's linking to the latest announcement on the announcements page, but generally this provides relevant short form updates to all users that you should be aware of. If you're ever curious about what's coming, be sure to check out these locations. And finally, under the Datasets tab, there is a new page called Archive Data. This is now the new location for all of our archive datasets. And please note that the Red Sea website has been decommissioned. So data including the TMY3 now reside at this new location and is available for download. This concludes my section, and I'll hand the mic back to manage it. Thank you.
Thanks, Nick. What I'll go to next is you've just seen what the current state of the NSRDB is. I will just quickly go through what our future plans are. So next slide, please. So as you've seen that our model versions have changed over the years, this basically is as a result of research conducted here at NREL to improve the model. what's in the pipeline now is the ability to calculate DNI in cloudy situations directly. So as most of you might be aware, that there are various ways of calculating the DNI when there's a thin cloud and there's still there's a direct beam, the solar radiation still available. But normally what happens is in the physical models originally, it only considered the attenuation as a pencil beam. And it does not consider the angular extent of the solar disk. Empirical models, basically, as they're empirical, they just get a relation between GHI and DNI, and it depends on the availability of data at various locations and time periods. Then there's the physical model, which numerically resolves the full rate transfer equation, and it's time consuming. Next slide, please. So this is what happens when we use the Beer's law to calculate the DNI, and the horizontal axis is the DNI as measured, and the vertical axis as modeled. As you can see that if we use the original models, it used to the pencil beam, the DNI is underestimated. On the other hand, if you use a model such as the disk model, which is a parameterized model, the DNI is overestimated, as it's obvious in these two plots. So we wanted to resolve this problem and get a better DNI into the NSRDB. So next slide, please. So what we did was we built a new model, which essentially computes the direct beam over an area which surrounds the disk of the solar disk, and then essentially integrate it to get the estimate of the DNI in different cloudy situations. Next slide, please. So what we did was we built a lookup table of cloud transmittances, and ultimately what we did was to make it even easier, we built parameterizations around that cloud transmittances, which essentially improves our ability to provide an accurate DNI in cloudy situations. This model will be implemented in our next version of PSM. So it will probably be a major update. So it would probably have a new version number. But again, as you've been hearing over from the various speakers, the data volumes are huge. While we implement the model in the new update of the data for, say, next year, we also have be cognizant that our model has improved, so we should at some point reprocess the data going back to 1998. So while this new model will be implemented, it is our anticipation that every 3 or so years we will reprocess the data so that the latest versions of the model is implemented for all our data. It's a big task, so we cannot do it as frequently as we would like. We cannot do it every year. So it has to be every around 3 years when all the data will be reprocessed, while the newest model will always be applied to the latest year of data when we do our updates. Next slide, please. Then finally, we just a quick glance at our publications. We try to make everything transparent, publish everything so that our users can refer and also read in more detail about our work on the NSRDB. So next slide, please. So here's a list of our recent publications. If you want to get a full overview of the NSRDB, there is the publication in Renewable and Sustainable Energy Reviews in 2018. The FARMS model has been published. There's also a publication on the spectral model, because NSRDB also has a service to make available spectral data through our website. Then finally, I just mentioned the new DNI model. We have, of course, published that. And then Grant talked about the machine learning the efforts to improve the NSRDB. paper was published in Solar Energy. So if all the NSRDB publications are listed on the NSRDB website, so if you really are interested in the full reference, it's available on this this link. In next slide. Then we have also a paper which analyzes the variability, because we have this long-term data set. So we wanted to understand what is the spatial and temporal variability of the resource. So this paper was also published in Renewable and Sustainable Energy Reviews, and is also available from the journal. The link is, of course, the full citation is, of course, available from our NSRDB website. Next slide. And that concludes our presentation. I hope you've liked to hear about our NSRDB, and we will be taking questions. And we finished a little early, so I guess we have a little bit of extra time for questions. Aaron Hapte is going to take over and moderate the Q&A session. So Aaron, please go ahead. Thank you, everyone.
And I will be saying the questions and also assigning one of the panelists to answer the questions. The first question is to manage it, and how do the GOES East and or GOES 16 and GOES 17 satellites compare?
So the GOES, it's the satellites, the technology is exactly the same. Both, it's just the location of the satellites. The GOES East satellite is sitting in the Atlantic Ocean over the equator, and essentially sees the mainland US. The GOES West satellite is sitting out in the Pacific and covers Hawaii and the western part of the US. There is overlap between the two satellites, but the channels and the technology is exactly the same, and both of them collect data at exactly the same spatial and temporal resolution.
Thank you, Manjit. And the second question is to you, Manjit, again. Is updated data for the PSA model regarding annual spatial and temporal variability available to the public?
The annual spatial and temporal variability, that data set is not directly available right now, but there's an effort ongoing to provide some of these summary statistics. That is a current effort. I've not mentioned that in our presentation, but we are putting in an effort so that we can make all this, instead of everyone having to compute it themselves, we are planning on making some of these summary statistics available to our users. Hopefully it should happen in the near future. We'll try to, I think that's the goal of our current project. So it's an activity we are currently involved in right now.
Thank you, Manjit. And the next question is Grant will start in the answer, and maybe Manjit you can add too. So the question is cloud top height for the parallax correction. I assume you derive from cloud top temperature, but how do you estimate cloud base height?
Yeah, maybe Manoj can comment. We use it's a cloud height variable out of the ACHA data set from University of Wisconsin. Manoj, I'm not sure if you.
So essentially, when we're doing the cloud shadow, it's primarily the top of the cloud. Assuming a parallel cloud, it's the top of the cloud which primarily matters based on where the shadow is. The bottom of the cloud will only influence situations where you have convective clouds. And in those convective cloud situations, we would see the side of those convective. Those situations are extremely complex and we probably have much higher uncertainty. We do not We could estimate the bottom of the cloud using some sort of estimate using the optical depth and distribute it through certain layers, but normally in normal situations, the uncertainty will be so high that it will not be able to improve the product. So the cloud top is what we currently use, and that gives us an estimate of whether it's a high cloud or cloud in around 6-7 kilometers or a low cloud, and that primarily drives the cloud shadows. Again, to remember is that if you have a cloud of large extent in a synoptic situation, frontal situation, covers a large area. Most of the benefit we derive from this cloud shadowing is for situations where there's patchy cloudiness and where the clouds are of extent of a couple of kilometers, which is our resolution. Essentially at this point, the cloud top height is all we have to work with. Hopefully that answers the question.
Thank you, guys. And the next question is to Grant, and then Manojit, you will follow up. Is version 3.22 available for Europe, Australia, South America, and other regions? How does the accuracy and reliability compare with US data? And maybe there were multiple questions also in this area. Manojit, maybe you can follow up after Grant in terms of CETO funded and international dataset funded, covering multiple regions. So Grant.
Yeah, so we processed most of the international data 1 or 2 years ago before the current version 3.22. So the international data is not going to include all of the updates that you just saw, or all the model improvements that you just saw. Most notably, it does not include the ML clouds method for gap filling. It's not going to include the variable snow albedo as a function of temperature. It's going to be a constant snow albedo. I cannot remember about the shading geometry, the solar shading geometry for parallax correction. But the most accurate way of like determining that is like when you go download that data, or when you go inspect those files, look at the version attributes of those files and then cross-reference with the version log.
All right. Yep. Thanks, Grant. And I'm just adding to differences between what happens with the CETO funded GOES data sets for the US. Essentially, that's our major project and our major focus, where so all the updates are any scientific improvements are always implemented on the GOES satellites first. Additionally, for the GOES satellites, we do the update every year, and it's an annual process. And as all of you know, for the GOES satellite, that's an annual process. For the USAID and DOE international funded, those funds are not a continuous process. So again, those are mostly done one time. And if there's an update by the funding agency, required update by the funding agency, and then funding will flow. And so it's intermittent for the for anything beyond the CETO funded projects. So and that's what you will see in the data too, that sometimes the data is only covers up to 2019 and there is no update for 2020 or 2021. And that's what the current state is of the NSRDB. Aaron?
Next question to Manojit. How does the NSRDB differentiate between cloud cover and smoke cover?
Cloud detection versus smoke is mostly part of the aerosol. So essentially, some of the channels, the satellite channels, I can identify ice and water. So the first part we do is identify whether it's a cloud or not. There's a cloud mask. The aerosols that cloud mask kind of tells us that these areas are cloudy or clear, and that's what with the current satellite algorithms, with all the available channels in GO 16 and 17, it does a pretty good job, even under reflective surfaces like when you see snow under the surface. And then after that detection is complete, the aerosols are sourced from MODIS, and we end up determining what their aerosol optical depth is in fire situations. Right now, we have an active project for detecting fires and understanding fires in California during the 2020 fire season. And apparently our algorithms work pretty well in distinguishing between fire and smoke. And that's mainly because of the additional near-infrared channels which are available from the current GHOST satellites. The previous satellites would probably have a harder time, but the newer satellites can discriminate between smoke and cloud.
Thank you, Manojit. The next question is to Nick, and then Manojit, you can follow up after Nick. The older version of NSRDB had other layers such as US counties. Is it possible to add such useful layers for solar developers to access? Probably terrain, slopes, tree cover, brownfields, etc.
Thanks for the feedback. The old viewer did include additional layers to help contextualize the solar resource. And so this is a valuable bit of feedback, and we'll definitely take that into account. At the moment, we've certainly prioritized data downloading rather than data exploration in the viewer itself for those contextual layers. But we're always looking to understand how people are using the tool. And so if that was a very useful pathway for using the viewer, then we'll definitely want to know that and take that into account. Manage it. I don't know if you have anything else you want to add.
Yeah, so again, like as Nick mentioned, that our primary focus at this point was to get our viewer updated and help our users seamlessly access the main data sets. Again, some of the additional layers, adding the additional layers is part of our plans, and that it will probably happen once we are able to complete our work in making the full data sets available. The one thing to note though is that if there is a layer which is more static, it's much easier for us to make available. If there are additional layers which have to be redone every year, given our current capabilities of funding and overall time available, those type of, if it's more dynamic and we have to update it every year, we probably will put it on a lower priority just because of the time and effort required. So just making you aware of how we use our limited resources as efficiently as possible.
Okay, thank you. The next question is to Grant, and then follow up for Manojit. You showed a model for Puerto Rico that synthesized higher spatial and temporal resolution data from a lower resolution source. Is this synthesis capability available for other locations?
The short answer is no. That data set and that project was specifically funded by the Puerto Rico projects that we have at NREL. It also uses some proprietary models for clear sky irradiance, REST2, that we are not able to release publicly. So it's a bit of a challenging model to release open source. We may have some ways to do that in the future using more advanced methods that don't rely on the REST2 model, but we have no plans to do so right now, unless Manojit has some plans that I am not aware of.
Oh, so essentially, just the model basically can be applied anywhere. That's so that's how Grant built it. That as long as we have a 30-minute data, it can be applied on any data. But the models used internally, as like Grant mentioned, we've not made it open source. It's a simple model. So it's but again, it's we could make part of it open source, but not the full version. So if the user would have to fill it in, and then we'll take it in that if the users are interested, we will take that into account, because there's a question, it seems like there's an interest in it. We will try to see what we can do to make it available. Please do send us any feedback at nsrdb@nrel.gov about what your interest is, if you're going to, what you'd need to be planning on using that model for, and we will definitely take this into consideration and see what we can publish. But we do not plan to downscale the data, full data, and make it available. That's for sure, because our data volumes are already significant. So imagine creating 5-minute data for all the years from '98 for all our satellites. That would be just a data explosion. So we don't plan on doing that, though. Thank you.
Okay, thank you. And the next question is to Manojit. I'm interested in modeling bifacial technologies for vertical 90-degree surfaces. Does the NSRDB have the data output for solar irradiance in kilowatt-hour per meter square per day on a vertical surface on north, south, east, west orientations?
No, the short answer is no. The NSRDB does not have make data available on vertical surfaces. What you get from the NSRDB is on a horizontal surface, the GHI, DNI, and diffuse. There's one data set available from the NSRDB which can produce data at different orientations. That is the spectral model, the output from the spectral model. So there is a link where you can get spectral data. I don't know, that might be a little overkill if you're just looking for broadband information. So what I would suggest is to use the NSRDB data from the horizontal and use some other model, downstream model. I don't know if Sam might also have that capability, or PVLib, if you're aware of it. PVLib would have various models where you can input the NSRDB data and produce the horizontal data sets. So that's my suggestion at this point. Thanks.
Okay. Thank you, Manojit. The next question is to Manojit, but everybody, the panelists, can contribute on this one. When will you publish a detailed documentation on the model and data sets, example time-step leveling conventions, explaining spatial and temporal sampling in data with intervals greater than 5 minutes, documenting height above ground of wind speed, etc. Much of this has been covered in previous webinars, in Q&A and GitHub, maybe in a journal article, but it really needs to be something like a user manual here in NSRDB website.
Agreed that we can definitely, all the pieces of information are available in different places. And I agree that we do not have a full comprehensive user manual covering all the aspects, all these questions in one document. And if I'm just repeating that Aaron, the question, in some ways you're looking for, okay, how we aggregate from 5 minutes to 30 minutes for our current data sets, that those pieces of information, I agree that we should make it available. So we're taking this on note. We've been updating our website, so we will definitely try to put this into a document and put it on our website. Our goal ultimately is to make as much information available, but also in a way that the document doesn't get dated. So we have to basically try to figure out the best way that the documentation is more dynamic, so the users it's easy for us to update and also for the users, so that the updates are done more frequently and quickly. But we definitely take this into account. Thank you for pointing this out, and we'll put some effort into this. Thank you.
Thank you, Manjit. And the next question is to Manjit again. Is the wind data set or wind speed attribute instantaneous? The documentation states that it is wind speed at the time indicated, which is a little unclear. If it is an average, is it finite difference average or long-term average or all of the minutes in that time window? So there were multiple questions similar to this too. I think maybe if you can answer it in kind of how the reanalysis data set is obtained also.
So essentially this, our wind data set comes directly from MERA2. It is the 2 meter, from what I recollect. I think it is the 2 meter wind speed, a 2 meter height wind speed. And this is what, just because it comes from MERA2, I would refer the user to documentation on MERA2. From what I believe that the wind data is available from MERA2 on an hourly basis, and we essentially downscale it by simple linear interpolation. So our wind data is not necessarily meant for any research on wind variability, because we just take wind data set from MERA2 and interpolate it to provide wind. It's a very simple way in which we present the wind data set. That's the caveat, because and it's mainly meant for use in PV modeling, which enables you to calculate the temperature of the panel. So for the users, the caveat is, advisory is, do not use it for anything more than that. But again, I'll refer you to the MERA2 documentation. We do not have any other better source of wind at this point, which you can use for our work. Hopefully that answers your question. Yeah, and go ahead, Grant.
The same is true for air temperature. So both air temperature and wind, and many of the supplemental variables are from MERA. So like a lot of people will use NSRDB for like buildings applications, and it's like, well, that's fine, but you have to understand that the air temperature and wind speed are not highly localized 4 kilometer, 2 kilometer data. They're more like 40 kilometer from MERA.
Yes, and we do some elevation correction with using lapse rate. So there is different, especially for the temperature, and also there are some physical corrections for the water vapor. But for the wind, especially, Grant, from what I can recollect, we just do a simple interpolation.
Yeah, it's pretty rough.
Yeah, it's pretty rough. So that's a full disclosure to our users. Thank you.
Thank you, guys. The next question is to Manjit. Is there a way to add a cloud edge enhancement in the future, particularly to the 5 minutes dataset? It doesn't appear that the existing dataset exceeds clear sky in a way that ground measurements do.
That's incredibly difficult, because those happen in very specific situations. Again, one thing to realize is that cloud edges are detected by measurement on the ground, which is a point measurement on the ground, which essentially sees different geometries with reflections from a cloud at which is on one side. If you're trying to understand what the satellite data is, the satellite data is essentially an average radiation over a 2-kilometer area. So imagine if you had 100 of these radiometers deployed in a 2-kilometer2-kilometer area, and you did an average. Would you really get cloud enhancement? Probably not. One or two of the instruments might show up a cloud enhancement. So that's one thing to think of, is that a satellite data set is provides essentially an average radiation over a certain area, and adding cloud enhancements, which is very difficult anyway, and adding any of that would be artificial and would not really represent what the satellite is supposedly doing. So no, we do not want to do something artificial, which is incredibly difficult at this point. Thank you.
Okay, thank you. The next question is to Grant. Could you please comment a bit more on the gap filling procedure after parallax and shading corrections?
Yeah, I'm not quite sure what they want me to comment on. I can quickly talk about it though, I guess.
Yeah, Grant, just a basic idea of the process. What you've published in the paper that's in
Sure.
more detail, but just a summary of what.
Sure, and then yeah, related to parallax correction and shading, maybe what the person's interested in is like, we have this satellite image, right, that is like a perfect image, and then we have clouds, but those clouds have elevation, and so when you parallax correct them, they move and they leave gaps. So maybe that's what they mean. But basically, like, we take the clouds and then we move them based on their geometry, the parallax correction, the shading, etc. We apply them on top of whatever is on those pixels. And then any gaps that are left over, we do like a nearest neighbor gap fill, and then we just remap everything to the original grid. And that kind of has been the best approach that we've found. There are some challenges, like with really tall clouds, you like literally can't see behind them, so you don't know what the cloud content is behind them. So like the nearest neighbor gap fill is kind of the best we've got. And then regarding the gap fill on the cloud properties, we have these traditional models. One's called DComp, the decomposition model that University of Wisconsin releases, and sometimes it just fails and has missing cloud properties. And the previous methods basically just took the nearest valid cloud property of the same cloud type, so ice or water, at that same site. So like if you're missing clouds on January 1st, cloud properties on January 1st, but you had valid cloud properties on January 2nd, you just take those cloud properties and write them over. But now we're using the machine learning methods to actually predict cloud properties from the satellite images themselves, and use that as a gap filling procedure. So that was a lot, but hopefully somewhere in there was what that person was looking for.
So yeah, and I just enhancing, just a quick comment on adding to what Grant said. So the physical models, what happens is because at high steep zenith angles of UV and steep viewing geometries, especially when the sun's at zenith angles 80 degrees, the cloud reflections are extreme in some ways. So what these physical algorithms have done traditionally is not produce a cloud property over where the zenith angle is above 80 degrees, and that means that it leaves us this gap, persistent gap above 80 degrees zenith angle. And like Grant mentioned, we were filling it using other days of data or other ways, simple interpolation methods, and now we've implemented the machine learning, actual cloud detection, the situation detection, which enables us to fill those periods much more accurately than previously. Aaron.
Thank you. And the next question is to Manojit. Can this new data set be considered bankable? If yes, please lay out the bankability factors.
No, well, first thing is the question is what what is bankability. That's basically, in a sense, it's basically taking the data to a bank. And so again, I'm not fully, that the term bankability for me is not as easily defined. But in our case, what we try to do is try to produce data and improve the quality of data as transparently as possible, and provide the validation to our users. It's for our users who essentially use the data to take it and validate it with their own ground stations, and demonstrate to a bank that it can be usable or not usable for any purpose, for their purposes. So our goal is not necessarily like to define bankability and work towards that goal. Our major goal is, primary goal is to use the state-of-the-art methods to provide data as accurate as possible. But again, as I mentioned previously, what a satellite sees versus what a ground station sees. If the only sole goal, even though we do our evaluation using ground measurements, and try to match it close to a ground measurement, a satellite sees an average over a certain area, and so inherently there is this difference in viewpoint, viewing geometries, which will have this level of uncertainty. And our goal is not to tune our data in any way. We do not do any site adaptation or tuning to match any ground station, because we believe that what we provide you, what the physics says of the average of solar radiation over a 2 kilometer or 4 kilometer pixel, and that's the information we can provide. So that again, bankability might require those fine adjustments and trying to match a ground station, but our goal is primarily not. That's not our primary goal. Our primary goal is to be able to get the best physics out and then compare it with the ground station to get it to the point where there are no significant biases. So hopefully that answers your question in a so anyway, so that's all I can say. But it's not our activity, not a direct activity to make data bankable. Thanks.
Thank you, Manojit. The next question is to you, Manojit. And any plans for releasing data set for the most northern locations, such as Alaska?
Yes, and again, it's a little bit of uncertain. We have been exploring ways to work with NASA, and who has a lot of expertise in the polar satellites, because the only way we can get data for the northern latitudes is to have stitched together a lot of polar satellites, and NASA does a lot of that work. So it's a collaboration we're working on to make that happen. Again, it will depend on where we can secure some funding to be able to essentially put that, make the models, create the latest models which will work for those northern latitudes essentially, and put it out. But it is something I have discussed. It is an active area of development. Major issue is which part of DOE or the government is interested enough to provide us the funding to make it happen. Thanks, sir.
Thank you, Manojit. The next question is to Nick, then maybe Manojit follow-up question for you. I just tried to download 2021 dataset, and the data is not available. So maybe, Nick, if you can answer it from a context of the 2021 data release, and also the upcoming reprocessed data release, maybe Manojit can follow up with that too.
Sure. 2021 should be downloadable for the USA and Americas at the 30 and 60-minute resolution at that 4-kilometer resolution, and we're still working on processing the rest of the years there. So that should be the full data set from 1998 to 2021. Hopefully in a couple of weeks. We're just experiencing some lags getting it onto AWS and through HSDS. So it should be for that specific one, it should be there, and the rest of the years will be coming shortly.
So just your question, Nick, is that the 4-kilometer, just clarification, 4-kilometer is available. The 30-minute data is the 5-minute 2-kilometer for 2021 that has not been made available yet. It's been put up on AWS. We're waiting to complete the full upload before we make the 5-minute data available. I think that's if the question from the user is that if they're looking for the 5-minute data, which probably not yet linked up. Is that just can you comment on that?
Yeah. So that's still in flight and should be hopefully in a couple of weeks time for the 5-kilometer, or sorry, the 5-kilometer data for 2021 should be in a couple more weeks.
All right,
So
thanks,
not
Nick.
yet.
Aaron.
Yeah, so we will take one more question, and then after that, I think we'll have a closing statement, and Jess will do that. The next question is for managers and Grant. Special variability question. In 8x8 grid, you would have quantity of 4 times 4 by 4 kilometer data set. Would this be considered spatially unique but temporally coincident?
So I've been reading that question. I wasn't sure what to say. I can take a stab at it while Manajit reads it maybe. Yeah, so like if observed from the satellite, like each one of those 4-kilometer pixels in your larger spatial domain is going to receive like a unique cloud property, solar radiance, etc. But obviously the clouds like move and transport around. And so I would say they are correlated, but spatially and temporally unique. I wouldn't say temporally coincident unless you're talking about literally like they all have the same time step, but they're not going to be the same value at any given time. Although they'll be, once again, correlated as a cloud moves through them, possibly.
I think that's what it is. It is correlated. It's even though each pixel is retrieved and calculated independently, the correlation definitely exists because that's what the satellite provides us. If it's cloudy and have the pixels, it's definitely that's what the real situation is. And temporally, again, it's like move from one time, it's instantaneous, so it's not an average. So again, we get an instantaneous snapshot, and the images are taking very fast, so it's practically well correlated. It's not like one pixel and the neighboring pixel, the timing is seconds. It's probably milliseconds. So it's pretty well correlated. But anyway, thanks, Aaron. I hand it over to you. I think we are at our time limit.
So yeah, thank you. The Q&A session will end here. Jess will do a closing remark and manage it if you have anything to add then.
Yeah, just a quick comment that there might be more questions. I don't know, Aaron has in his repository. We will definitely make it a point to answer all the questions and put it out, send it out to everybody who joined, so that you have an answer. It'll take a couple of weeks maybe, so that as we go through everything, but we'll definitely we'll answer all your questions. Thank you everyone for attending. We really appreciate that so much interest. So Jess, please take over.
Thanks so much, Manajed. And thank you again to everyone who joined us today. We so valued your input and your questions. I did want to give a friendly reminder that we were recording today's session. We're going to process that recording and the presentation deck that you've been viewing, and we will not only add those to the NSRDB website, but send them out via email to anyone that registered today. So even if you were here and only for a short time, you'll be able to get a direct email to access those items. Otherwise, again, thank you so much for joining us. We loved having you here today, and I'm going to go ahead and close this out. Thank you so much.
Thank you, everyone, and bye.